Good day, everyone. So, for today's topic, we will talk about phase changes, and it will be discussed by me along with topic James Carlo. So, let's begin. A phase is defined as a homogeneous state in which substance has a uniform composition. So, basically, it is a homogeneous because only the appearance or phase state change, and we all know that there are three fundamental phases of matter, which are solid, liquid, and gas. And for example, the mixture of salt and water, an example of homogeneous mixture. And when you put it on a refrigerator or in a freezer, it will turn into an ice or solid state, but the components are still the same and it is still composed of salt and water. So this is the representation of the phase of matter, the solid, liquid, and gas. Now let's proceed with the phase changes. So as you can see in the picture, there are the three fundamental phases of matter: the solid, liquid, and gas. So let's begin with the first one, the melting. So melting happens when you apply heat on a solid substance and it will turn into liquid. Like for an example, an ice. When you apply heat to an ice, it will turn into water. And next, the boiling or evaporation process. So when you apply heat from water, it will evaporate and it will turn into a gas. And the next one, the condensation. The condensation, it is the reverse process of evaporation, where the evaporated evaporated water will turn into a water once it is being cold. Yeah, like that. And the next one, the freezing. So when the liquid being applied with cold, like when you put it into a freezer, it will turn into an ice or solid state. Molecular order in phase changes. In solids, molecules are well ordered and are not free to move around. When a solid transitions to a liquid or gas, there is a decrease in the order in the material. It is because solid is well compact, and if you turn it into a liquid state, it is lessened or decreased, and there's a space for them to move. And same with the gas. So if the liquid turns into a gas, they will be they'll have more space for them to move. Energy in phase changes. So with the form of heat, the phase changes when heat is added or being taken away. When an ice melts, molecules shift from an ordered structure to a less ordered one. In other words, heat is absorbed, and it is called the endothermic process. So, in endothermic process, as what I have said before, heat is absorbed. The amount of heat energy transferred from the surroundings to the substance is a change in enthalpy. An enthalpy is the sum of the internal energy and the product of pressure and volume. And it is represented by the symbol of triangle H, but this is read as delta H. For an endothermic process, the change in enthalpy is always positive, or delta H is greater than 0. In general, a phase change is in the endothermic if the molecules are more disordered. So the next one is the exothermic process. Exothermic process is the opposite of endothermic. In exothermic, heat is released to the environment. The change in enthalpy will always be negative, or delta H is less than 0. In general, a phase change is exothermic if the molecules are become more ordered. When we say more ordered, is more compact, or there's not there's not enough space for them to move. Did you know that endo, exo, and thermos was derived from the Greek word endo, it means inside, and exo, it is outside, while thermos is equals to heat. When heat is absorbed, it is endothermic. Heat enters the system. So the key word from here was the en, that means enters. Oh, heat enters the system, like that. So, and for the exothermic, when heat is released, it is exothermic. Heat exits the system. So the keyword from exothermic was the ex from exit, or the heat exits the system. Specific heat. Now, um, there's always a specific heat needed to 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 change the pace of a substance or matter. The temperature of a substance is independent to the amount of material, since it is a measure of the average kinetic energy of each particle in the substance. However, the amount of heat will depend on the quantity of material. The amount of heat needed to increase the temperature of a specific substance by 1 degree Celsius is defined as specific heat. In the case of water, the specific heat for ice is 2.00 joule per gram degree Celsius. And for liquid water, it is 4.186 joule per gram degree Celsius. And for water vapor, it is 2.11 joule per, joule per gram degree Celsius. Enthalpy and phase changes. In endothermic processes like melting and evaporation, energy is applied to break the intermolecular attractive forces that holds the particle in their present state, or in other words, with the form of heat. The temperature at which a substance turns from solid into liquid is called the melting point. Another term for the melting process is fusion. The amount of heat needed to melt a substance is called the heat of fusion, or the enthalpy of fusion, symbolized by delta H fuzz or fusion. The reverse process is freezing, and the temperature where this occurs is the freezing point. The melting point and the freezing point of any substance is the same. The temperature at which liquid turns to gas is called the boiling point. The amount of heat needed to complete the phase change of a substance is called the heat of vaporization, or the enthalpy of vaporization, symbolized by delta H vap or evaporation. If you add heat energy to a solid at its melting point, or a liquid at its boiling point, the temperature of the substance will remain constant under constant pressure. Enthalpies of phase changes are commonly calculated in kilojoules per mole, and in this case, it is called the molar enthalpy of fusion and the molar enthalpy of vaporization. Uh, there are also enthalpy values calculated on a per gram basis. Calculations involving energy changes. There are two situations we have to consider in calculations involving energy flow in and out of material. In calculations where no phase changes are involved and under constant pressure, the amount of heat is just calculated by the means of the equation in the screen, where Q is the amount of heat energy in joule, M is the mass in kilograms, and C is the specific heat, and change of time I change of triangle T is the change in temperature. In calculations involving purely phase changes under constant pressure, the amount of material in moles is simply multiplied to the molar enthalpy of the particular phase change. In other words, where Q is the amount of heat in joules, N is the amount of the substance in moles, and triangle H is the molar enthalpy of the process, whether freezing, melting, evaporation, condensation, in joules per mole. When we say triangle H, it is the change of um, enthalpy. Now, let's have a problem. So the problem is how much energy is required to raise the temperature of a 70 grams of water in the liquid state by 12 degrees Celsius if the specific heat of water is 4.186 joule per gram degree Celsius. So the first one, or the step one, is identify the given. The given in the problem is change of temperature is equals to 12 degrees Celsius, M is equals to 70.0 grams, and C is equals to 4.184 joule per gram degree Celsius. Step 2. Identify what is asked in the problem. The problem asks for the amount of energy in increasing the temperature of a substance without undergoing phase changes. Step 3. Write the working equation, where Q is equals to mc change of temperature. So in step 4, substitute the values and solve the amount of energy, where Q is equals to 70.0 gram, and that is the M, and 4.184 joule per gram degree Celsius is the C, and for the change of temperature, it is 12 degrees Celsius, and when you solve it, it will be 3516 joule. The degree Celsius is being cancelled here, so the answer only will be 3516 joule. So step 5, it will be the final answer. The final answer was 3516 joules. Therefore, the amount of energy required for this process is 3516 joules. And that's all for lesson 1, unit 2. Thank you for listening. Hello and welcome again to our video reporting. So, for today's topic, we're going to continue the lesson, and which is the lesson 2, the phase diagram, that will be reported by me along with James Carlo topics. So, let's start. A phase triangle is shown in the picture, which summarizes the enthalpy change for phase change at a specific pressure and temperature. So basically, the transformation from a more compact, or let's say more condensed space, to a less condensed space, like for example the solid to liquid, which is the melting process, that requires energy in the form of heat, and these transformations are endothermic. While on the other hand, changes from a less condensed space to a more condensed space, for example, gas to liquid, which is the condensation process that releases energy, and these transformations are exothermic. And the energies associated with these transformations are reported as enthalpy change. Each phase change occurs at a particular temperature and pressure. Like for example, ice melts at 0 degrees Celsius melting point at around 0.006 atomic mass. Water boils at 100 degrees Celsius boiling point at about 1 atomic mass, but the opposite phase change also co-occurs at this temperature and temperatures and pressures. Water also freezes into ice at 0 degrees Celsius and 0.006 mass, and water vapor also condenses at 100 degrees Celsius and 1 atomic mass. At the specific temperatures and pressures, phases coexist. The rates of opposing simultaneous phase changes are equal. This condition is known as dynamic equilibrium or simply equilibrium. In liquid vapor equilibrium, our example for this is a cup of water. When we left it open in the air, it evaporates with the power of heat and escapes to the atmosphere. However, in a closed container, the resulting vapor accumulates in the space, and at this initial stage, evaporation takes place. Some of the vapor molecules grow as the liquid creates more. Their potential to collide and their potential to collide with and become stuck in liquid molecules cause them to condense. As space gets smaller, the intermolecular forces of attraction get stronger. Dynamic balance is established when the rate of evaporation and condensation are equal. And in this picture, it shows the rate of evaporation and rate of condensation before and after dynamic equilibrium is established. Did you know why does it feel cold when you rub alcohol in your skin? Isopropyl alcohol is a common component of rubbing alcohol, and it is highly volatile and has low enthalpy evaporation. Upon contact on the skin, it evaporates quickly and extracts the heat, producing the cold feeling. If the values of enthalpy evaporation and the vapor pressure at a given temperature are given, one can solve the vapor pressure at a given temperature using the two-point form of the Clausius-Clapeyron equation. The Clausius-Clapeyron equation is P1 over P2 is equals to enthalpy evaporation over R parenthesis 1 over T temperature 2 minus 1 over temperature 1 close parenthesis, where P1 is the vapor pressure at T1 and P2 is the vapor pressure at T2. Vapor pressure can be expressed in any pressure unit. The temperature must be in kelvins. R is the gas constant with a value of 8.3 3145 joules per mole. Ulit. R is the gas constant with a value of 8.3145 joules per mole, exponent -1 times Kelvin -1. This form can also be used to approximate the enthalpy evaporation given two datasets. Now let's have a problem using the Clausius-Clapeyron equation. So the problem here, the vapor pressure of water at 343.15 Kelvin is 0.3075 atomic mass. And what is its vapor pressure at 373.15 Kelvin? The molar heat of vaporization of water is 40,790 joules per mole. So for the solution, step 1, identify what is asked in the problem. You are asked to calculate the vapor pressure of water at 373.15 Kelvin. So for step 2, identify the given in the problem. So the vapor pressure at 343.15 Kelvin and the final temperature and the molar heat of vaporization are given. So P1 is equals to 0.3075 atomic mass and T1 is equals to 343.15 Kelvin and T2 is equals to 373.15 Kelvin, and enthalpy vaporization is equals to 40,790 joules per mole. So for step 3, write the working equation. So the Clausius-Clapeyron equation is P1 over P2 is equals to H bar over R parenthesis 1 over T2 minus 1 over T1 parenthesis. But we are looking for the vapor pressure. So to find the vapor pressure, we'll use the P2 is equals to P1 over enthalpy vaporization over R parenthesis 1 over T2 minus 1 over T1. Then now we'll go to the step 4. Step 4, we're going to substitute the given values. Now that we have substitute the given values, we'll proceed to the calculation. After you solve it, for step 5 will be the final answer, which is the V2 is equals to 0.9706 atomic mass. And the vapor pressure of water at 207.53 over 0.15 Kelvin is 0.9076 atomic mass. And that's all for the equilibrium nature of phase change to Clausius-Clapeyron equation. And the next lesson will be tackled by James Carroll topic, which is the solid to liquid equilibrium to phase diagram. And thank you for listening.
Good day everyone, I'm James Topic and this is the continuation of the report about phase triangle. Now let us proceed to the solid-liquid equilibrium. Solid-liquid equilibrium. Melting and freezing can also be described as a dynamic equilibrium between solid and liquid phases. Ice and water coexist at 0 degrees Celsius and 1 atom. At this temperature and pressure, ice melts and water freezes simultaneously at the same time. So, in solid-liquid equilibrium, the energy required to melt 1 mole of a solid is called the molar heat of fusion. It is usually smaller in magnitude in comparison to heat of vaporization, since the change in packing arrangement from solid to liquid is less drastic than that from liquid to gas. Next is solid-gas equilibrium. Solid-gas equilibrium. Some solids can become gas without passing through the liquid phase. Sublimation is the direct transformation of substances from the solid phase to the gas phase. Dry ice or the solid carbon dioxide, iodine crystals, and mothballs or the naphthalene readily sublime at observable temperatures and pressures. These substances have relatively high vapor pressure at temperature below its melting point. At their sublimation points, sublimation and deposition simultaneously occur at equal rates, as governed by the following dynamic equilibrium. So, in solid-gas equilibrium, the energy required to sublime 1 mole of a solid is called the molar heat of sublimation. It is calculated using the equation molar heat of sublimation equals to the molar heat of fusion plus molar heat of evaporation. Next is the phase diagram. So, a phase diagram describes the phase of a substance at a particular temperature and pressure. A phase diagram also shows the phases of a pure substance as pressure, or the y-axis, is plotted against temperature, or the x-axis. The pressure in the diagram can be either the one applied to the system or the one generated by the substance. Next is the phase diagram of water. So, the phase diagram of water. Unlike phase diagrams of most substances, the melting curve in the phase diagram of water is slightly slanting to the left, with a steep slope. This observation suggests that the melting of ice is mainly dependent on changes in pressure and independent on changes in temperature. You can melt an ice cube by applying pressure using your hands. So, this unusual behavior is a consequence of the fact that water is denser than ice. And in phase diagram of water, another notable feature in the phase diagram of water is polymorphism, in which solid exists in several forms. The solid water in the phase diagram is called the ice 1 and exists at normal pressures. Other forms of ice is 1 to 7 exist at very high pressures. For instance, ice 1 and ice 3 and the liquid water are in equilibrium with one another at negative 22.0 degrees Celsius and 2045 atoms. Next is the phase diagram of carbon dioxide. At negative 56.4 degrees Celsius and 5.11 atoms, carbon dioxide exists in all three phases. That the pressure at the triple point is relatively high, which explains why carbon dioxide does not exist as a liquid, hence the dry ice, and readily sublimes under observable conditions. The melting curve in the phase diagram of carbon dioxide is leaning to the right, which suggests that the liquid phase is less dense than its solid phase. So in these phases of carbon dioxide, the carbon dioxide existed in all three phases, and this pressure at the triple point is relatively high. That explains why carbon dioxide does not exist as a liquid. So also in this lesson, always remember that in a solid liquid equilibrium, freezing or fusion and melting occurs at equal rates. The energy required to melt 1 mole of a solid is called the molar heat of fusion. In a solid gas equilibrium, deposition and sublimation occur at equal rates. The energy required to sublime 1 mole of a solid is called the molar heat of sublimation. Also, a phase diagram describes the phase of a substance at a particular temperature and pressure. A phase diagram of water can be used to explain the notable properties of water, such as the density and polymorphism of ice. The phase diagram of carbon dioxide can be used why CO sublimes at observable conditions and why it is a good supercritical fluid. And that's all I report about lesson 2.2. Thank you for listening. Heating and cooling curves. Transformations or substances in real life involve multiple phase changes and temperature changes. There are instances when a substance in its solid state is converted into its gaseous state. In between phase changes, additional heat is needed to reach the temperature from the melting temperature to the boiling temperature. Next, the one shown in the screen is the heating curve for water. So the amount of heat in complex phase transformations can be tracked in heating and cooling curves. In these curves, the temperature y-axis is plotted against total heat changes, or the x-axis. An example of a heating curve is shown on the screen. The heating curve in screen shows the heat associated with the transformation of 1 mole of ice initially set at negative 25 degrees Celsius and 1 atom to steam at 125 degrees Celsius and 1 atom. The amount of heat can be calculated by adding all heat absorbed from each phase and temperature change. The process can be divided as represented by the segments. So the blue segments represents temperature changes without phase change, while the red segments represent phase changes without temperature change. Next is the segment AB. So this segment AB represents a change in temperature of ice from negative 25 degrees Celsius to 0 degrees Celsius. The heat associated with an increase in temperature can be calculated using the equation on the screen. A mole of ice weighs 18 grams and the specific heat of ice is 2.108 over grams by degree Celsius. Next is segment BC. So the ice cube starts to melt from point B and ends with point C. Since there is no change in temperature during phase changes, segment BC as well as the other phase changes appears horizontal in the phase diagram. The heat associated with phase changes can be calculated using the equation on the screen. Ice has a heat of fusion of 6000 J over mole. Next is segment CD. Segment CD represents a change in temperature of water from 0 degrees Celsius to 100 degrees Celsius. The heat associated with an increase in temperature can be calculated also by using the equation on the screen. A mole of water weighs 18 grams and the specific heat of water is 4.184 J over gram by degree Celsius. Next is segment DE. Segment DE, water starts to boil from point D and ends with point E. Since there is no change in temperature during phase changes, segment DE as well as the other phase changes appears horizontal in the phase diagram. The heat associated with phase changes can be calculated using the equation on the screen also. Water has a heat of vaporization of 40,700 J over mole. Last is the segment EF. Segment EF represents a change in temperature of steam from 100 degrees Celsius to 125 degrees Celsius. The heat associated with an increase in temperature can be calculated using the equation on the screen. So, a mole of steam weighs 18 grams and the specific heat of steam is 1.97 J by gram negative 1 times degree Celsius by negative 1. It should be noted, however, that the heat is additive in each process. The heat required on the phase transformation from point A to point C is the sum of the heat calculated in segment AB and BC. The overall heat associated with the transformation of 1 mole of ice initially set at negative 25 degrees Celsius, and 1 atom to steam at 125 degrees Celsius, and 1 atom is the sum of the heat calculated for all line segments. So, to create a heating curve, one must plot temperature or the y-axis against the heat or its x-axis. Processes where heat is absorbed to increase temperature are represented by lines slanted upright, while horizontal lines represents changes or phase changes at a constant temperature. Cooling curves are the exact reverse of heating curves. Instead of absorbing heat to increase the temperature, heat is released in cooling curves. So, processes that require the release of heat are represented by lines sloping downwards, while horizontal lines still represent phase changes. A cooling curve can be produced from the heating curve presented in the screen by reading the plot from the top right to the bottom left. So, the opposing phase changes, an example of this is the condensation and the freezing that occurs, and the molar enthalpies associated with this phase change in cooling curves. Cooling curves have the same magnitude but opposite in sign compared to those in heating curve. So in this lesson, also remember that heating and cooling curves are used to track heat changes associated with complex phase transformation. And a heating curve is produced when the temperature changes y-axis are plotted against heat changes or the x-axis. A cooling curve can be constructed from a heating curve by reading the latter from top right to the bottom left. And that's all of our report of lesson 2.3 about heating and cooling curves. Thank you for listening.